Okay, let's unpack this. If you're knee-deep in engine development, or maybe just using an engine like Unreal Engine and wondering about the magic, about macros like UClass and generated body.
Yeah, those things you sprinkle in your C++.
Exactly. You put them in your C++ classes, you run some build step, and bam, suddenly your custom code is, visible to the engine.
In the editor at runtime.
All sorts of cool reflection powers just kick in.
Yeah, right.
But what is that build step actually doing? How does it bridge your C++ source code to the engine's dynamic runtime world?
Well, it's definitely not magic as much as it sometimes feels like it. It's code generation, plain and simple. Behind the scenes, there are build tools, often scripts, that parse your C++ header files.
Just plain text files.
Right. They look for those specific macros. UClass usually extract key information, and then they actually write companion C++ files.
The .generated.h and .generated.cpp files.
Precisely. And those files provide the necessary plumbing, the boilerplate code, for the engine's reflection system to work with your types.
Exactly. And to kind of peek behind that curtain, we're doing a deep dive today into, the idea of a specific piece of code. A hypothetical tool, let's say a Python script, designed to illustrate exactly this process.
Okay.
Its job is to parse C++ header files, find the UClass macro, and generate those .generated files to provide what we'll see is often called minimal reflection info.
Focusing primarily on the StaticClass functionality, I bet.
You got it. So our source material for this dive is, conceptually, a script like that. Think of this script as a simplified, understandable model of what a more complex engine build tool might be doing.
Makes sense. Like a teaching example.
Right. We're going to go through it piece by piece, understand its logic, its mechanics, and really importantly, dissect the structure and the purpose of the C++ code it creates for your classes.
So our mission is basically to pull this hypothetical script apart, to understand why this kind of code generation even exists, and what minimal reflection looks like at a really fundamental level. We'll follow the script's flow, right? How it gets started, how it reads and understands your headers.
Yeah.
And then the big part, detailing exactly what C++ code ends up in the .generated.h and .generated.cpp files.
Cool. So, Chapter 1, the script's foundation and entry point. Diving right in, the very first line you'd often see in a script like this on Linux or Mac is #.usurbanenv Python 3. What's that telling us?
The shebang line. It's standard Unix-like stuff. Basically, it's a directive for the operating system.
Okay.
It tells the OS, hey, run this file using the Python 3 interpreter. The env command helps find where Python 3 is installed on the system. It just makes sure the script runs with Python 3 if you execute it directly, like .myscript.py.
Got it. And then right after that, you usually find a multi-line string.
The doc string, yeah. It's like the script's built-in help text. It gives you the high-level summary. For a tool like this, it might say something like,
parses specified C++ header files for UClass macros and generates corresponding .generated.h and .generated.cpp files containing minimal reflection info, StaticClass implementation. Expects header paths as command line arguments.
something like that.
Exactly. Short, sweet, tells you what it does and what it needs.
Okay, that phrase, minimal reflection info, StaticClass implementation, tops up again. From an engine dev perspective, what is reflection, really, and what does minimal imply here?
So reflection in an engine context is basically the engine's ability at runtime to look at and interact with your C++ types, your classes, properties, functions.
Without needing to know the exact C++ type at compile time everywhere.
Precisely. It's how the engine can, say, find your Agamemnon class just by using its name as a string, or how the details panel in the editor can show the properties of an object you've selected. That's all reflection.
Minimal, in this context, based on that docstring, tells us this specific script isn't trying to do everything. It's focusing on the absolute basics needed for the engine to recognize the type exists, specifically generating the code required for the StaticClass function.
Right, StaticClass. You see it everywhere in engine code bases. I call it on my UClasses all the time, but what fundamentally is it doing?
So StaticClass is a static member function. It gets automatically added conceptually to every class you mark with UClass. When you call, say, UEMini stat class, it returns a pointer.
A pointer to what?
A pointer to a unique engine object, specifically an object of type UClass. That UClass object is the engine's runtime representation of your UEMini C++ class. Think of it as the central hub holding all the metadata about your type, its name, its parent class, and in a more complete system, lists of its properties, functions, all that stuff.
Okay, so this script we're talking about is designed specifically to generate the C++ code that makes that StaticClass function exist and work correctly for your classes.
That's the core goal, yes, for this minimal version.
Got it. Now, to do its job, the Python script needs some standard tools.
Yeah.
We'd expect imports like o's, re, sys, and maybe pathlib.path.
Absolutely essential utilities. OS gives you operating system functions, checking if files exist, creating directories, that kind of thing.
Right.
Re is the regular expression module, absolutely crucial. That's how the script is likely scanning the text inside your C++ headers to find the patterns it cares about, like UClass.
A pattern matching engine.
Yep. Sys provides access to system-level stuff like the command line arguments the script was run with, sys.rgv, or functions for exiting the script, sys.exit.
And pathlib.path. I like pathlib.
Me too. It's a much nicer, more object-oriented way to handle file system paths compared to just manipulating strings. Makes joining paths, checking existence, getting parts of the path cleaner, and less prone to errors, especially across different operating systems.
Definitely good for robustness.
Okay.
Okay, so those imports set the stage. The script's execution then typically starts in a main function.
Correct. Main is the standard entry point in Python. It orchestrates the whole process.
And the first thing main usually does is look at sys.rgv. What's it checking there?
Sys.rgv is just a list of the words you typed on the command line to run the script. Sys.rgv is the script's own name. So if the script checks something like len sys.rgv2, it's checking if you provided any arguments after the script name.
Because it expects.
It expects you to give it the paths to the C++ header files you wanted to process, like Python generate my headers.py, source my game my actor.h, source my game my component.h.
And if I just run Python generate my headers.py with nothing else?
The length is only one, just the script name. It'll probably print a helpful usage message, usage.python generate my headers.py, header1.h, header2.h, and then it'll likely call sys.exit1.
Exiting with an error code.
Right. The non-zero exit code signals that something went wrong, in this case, missing required input. Standard practice.
Okay, but assuming I do give it some header paths.
Then it collects them. A line like header paths equals sys.rgv1 basically grabs everything from the second argument onwards and puts them into a list called header paths.
And it probably prints a little feedback message like processing 2 header files.
Yeah, usually. Printf, processing len, header paths, header files, specified on command line. Good practice, tells you it understood the input.
The core of main then seems to be a loop. It iterates through those header paths. Inside, it calls another function, maybe process header file, and collects the results in a list. Let's call it all class infos.
Exactly. You can picture main as the manager. It gets the list of header files, the tasks, and for each one, it hands it off to a specialist function, process header file.
The parser function.
Right. That function's job is to take one header file path, open the file, read it, and figure out if there is any UClass definitions inside that need processing. It finds the relevant info and typically returns a list of data structures, one for each class found in that file. And main just loops through, calling this worker for each file, and uses something like .extend to add all the results from each file into one big master list, all class infos.
After processing all the files in the loop, there's likely a check. Something like, if not all class infos.
Yeah, that's checking if, after looking through all the headers you provided, the master list, all class infos, is still empty.
Meaning
It didn't find any UClass definitions that met its criteria for generation in any of the files. If that's the case, it should print a specific message like, no UClass definitions found needing generation in the specified headers, and then exit cleanly, probably with sys.exit, 0. No error, just nothing to do.
Makes sense.
Yeah.
But if it did find UC classes, so all class infos is not empty.
Then the work begins. It takes that list, all class infos, which now contains all the structured data about the classes to generate, and passes it to the next major function, maybe called generator reflection files.
The generator function.
Precisely. That's the function that will actually write the .generated.h and .generated.cpp files.
And the very final output from main would report the counts returned by that generator function.
Yeah, a summary message. Something like, print and successfully generated generated.h files and generated.generated.cpp files. Clear feedback that it finished and what it produced.
And lastly, that standard Python thing.
Yeah.
If name equals main.
Yep. Very common idiom. And just make sure that the code inside that block, which is usually just the call to main, only runs if you execute the script directly. If you were to import this script as a module into another Python file, the main function wouldn't run automatically. Keeps things tidy.
Okay, let's pause here for a quick recap. We've looked at the script's entry point, the main function. Its job is clear. Grab header paths from the command line, loop through them, delegate the parsing of each header to a process header file function, collect all the findings about UClasses into a list, check if there's anything to do, and if so, pass that list to a generator reflection files function to actually write the output files. It handles the basic command line stuff and orchestrates the main workflow. This sets the stage perfectly for the two main acts, parsing the headers and then generating the code.
That's a great summary. Main is the conductor, getting everything ready for the parsing and generation phases.
Right. So let's move to Chapter 2, parsing the header files. The focus shifts now to that worker function, let's call it process header file. Header paths .txt, this is where the script actually reads and analyzes your C++ code.
Exactly. This function gets called once for each header file path provided on the command line.
It probably starts with some path handling, maybe using pathlib again. Like header path is to your path. Header path str.resolve.
Very likely. Takes the input path string, turns it into a proper path object, and calling .resolve is good practice. It makes the path absolute, handles any symbolic links, so you're working with a definitive, unambiguous path to the file.
So maybe another print statement for progress. Processing header. Some relative path myActor.h.
Yeah, print if processing header path.relativepath.cwd. Using relativepath.cwd makes the output cleaner, showing the path relative to where you ran the script, which is usually more readable than a super long absolute path.
Then some basic validation, right? Check if the file actually exists and is a file.
Absolutely. If not, headerpath.exists, or not headerpath. Essential sanity check. If the path doesn't point to a real file, it should print a warning, like, cannot find or read header file. And just return an empty list immediately. No point trying to process something that isn't there.
Okay, assuming the file is valid, it needs to read the content. Probably a try, that's a block around an open call.
Exactly. You'd see something like try with open header path, R encoding UFF8 as F content, elif.read. The R is for reading. Specifying encoding UFF8 is vital for C++ source files, which might contain non-ASCII characters and comments or strings.
And the with statement handles closing the file automatically.
Yep. Ensures the file is closed even if errors happen during reading. The try.except block around it would catch potential I/O errors or Unicode decode errors if the file isn't valid, UTF-8, print an error message, and return an empty list, preventing the script from crashing on bad input files.
Okay, so now it has the entire content of one C++ header file loaded into a single string variable, content. The real magic, or rather the core logic, then comes from using regular expressions, right? So it'd be some complex pattern defined, maybe like UClass plus API say, DBCAS, the W plus Baplix is all intense.
It is intense, but it's the heart of this simple parsing approach. This regex is like a highly specialized search query designed to find exactly the pattern of a UClass. Macro call, typically on one line, followed immediately on the next line by a C++ class definition that includes public inheritance.
Symmetry, like digital metal detector specifically tuned to ping when it finds that UClass signature next to a class name, public parent line.
Oh, that's a great way to put it. A very specific ping. Let's break down that regex pattern piece by painful piece.
Roll for it.
UCLS. Okay, this finds the literal word UCLS. CLASS means 0 or more white space characters, spaces, tabs, matches the opening parenthesis.
Right.
Matches any character that is not a closing parenthesis, 0 or more times that grabs whatever parameters might be inside UCLS, and matches the closing parenthesis. So finds UCLS, or UCLS blueprintable.
Got it. Finds the macro call.
N. After the closing parenthesis of UCLS, this matches any character except a new line, 0 or more times, effectively consuming the rest of that line. Then it matches the actual new line character. This assumes the class definition starts on the next line.
Okay, moves to the next line.
Class plus hair. Now we're expecting the class definition. S plus matches any leading white space on the new line. Class matches the literal word class. S plus matches one or more white space characters after class.
Finds class, basically.
W plus API is
API.
This part's tricky. Creates a non-capturing group. The S at the end makes this whole group optional. Inside, W plus API is the first capturing group. W plus matches word characters, letters, numbers, underscore. So it looks for something like engine API or mygame API. S plus requires one or more spaces after the API macro if it exists. So this whole chunk optionally finds and captures an API export macro if it's right between class and the class name.
Captures the API macro if present.
W plus. This is a second capturing group. W plus matches one or more word characters. This is designed to capture the actual C++ class name, like Amy Player Controller.
Captures the class name. Crucial.
Matches the inheritance part. S for optional space. Drac for the colon. S again, the literal word public. And S again looks for public S.
Finds the public inheritance specifier.
W plus. And finally, the third capturing group. W up plus matches one or more word characters again. This captures the parent name of the class being inherited from, like a player controller.
Captures the parent class name. Also crucial. Ooh. Okay, that regex is doing a lot of work, so the script then uses re.findle with this pattern.
Exactly. Matches re.findle. UClass pattern content re.multiline rs.final scans the entire header content string and returns a list of all the places where that pattern matches. Because our pattern has those three capturing groups for the API macro, class name, and parent name, findle returns a list of tuples. Each tuple will contain the three captured strings for one match found.
So a list like nginiapi, amiactor AAC, move my component, uactor component.
Precisely. Notice the first element in the second tuple is empty. That's because the optional API macro group didn't match for UMyComponent in that hypothetical case.
Yeah.
The re-multiline flag is often included. It changes how and anchors work, making them match start end of lines, not just start end of the whole string. Might not be strictly needed for this pattern, but good practice when dealing with multi-line text.
What if it runs findle and gets an empty list back? No matches found in this header.
That's handled by if not matches. If the list is empty, it means the specific UClass followed by class public pattern wasn't found. The script should print a message like, no UClass definitions matching pattern found in this header, and process header file just returns an empty list. No class is found here.
But if match is populated, it loops through that list of tuples for API macro, class name, parent name, and matches.
Right. It unpacks each tuple found into those three variables for processing within the loop.
And there's some logic you mentioned to handle the API macro if the regex capture was empty. It tries to guess based on the file path.
Yes, that's a common fallback or heuristic you might see in a simpler tool. The regex tries its best to grab the API macro if it's right after class, but code styles vary. So, if API macro comes back as an empty string from the regex match, if not API macro, the script might look at the header path tree itself.
Like string searching.
Yeah. If the path contains engine source runtime, maybe it assumes the macro should be nginiapi. If it contains engine source editor, assume editorapi. If game source, maybe assume a game-specific one like mygameapi or like in the example UEMini Generated.
Yeah.
And if none of those match, maybe it just defaults to engine API as a last resort.
That path guessing feels a bit brittle, doesn't it? What if my project structure is different?
It is brittle. You've hit on a key limitation of simple regex plus heuristic parsing versus a full C++ parser. Real engine tools like Unreal Header Tool, UHT, do much more sophisticated analysis. Understanding include paths, preprocessor defines, maybe even building a partial abstract syntax tree, AST. This script's approach is a simplification, making assumptions about project structure and code style. It works for a specific setup, but isn't universally robust.
A necessary compromise for simplicity in this example, maybe. Okay, and it also needs to figure out the include name for the parent's generated header. There was that mapping logic.
Right, a simple lookup table, usually an ifalse block. The generated code for your class, say AMyActor, will need to include the generated header for its parent, AActor. So the script needs to know that if the parent name is AActor, the corresponding generated header stem is actor, leading to actor.generated.h.
So have mappings like parent name, uObject maps to parent header stem, object, parent name, AActor maps to parent header stem, actor, parent name, uActor component maps to actor component, and so on for common-based classes.
Exactly. It's just encoding the expected naming convention for the generated files of common engine types.
Okay, so for each match found and processed, it gathers all this info. The original header path, the derived generated include a name, like myactor.generated.h, the captured class name, the captured parent name, the looked up parent header stem, and captured or guessed API macro, and packages it all up.
Into a dictionary, typically. A class info dictionary for each UClass found, holding all those pieces of data the script needs for the next stage.
Header path, generated include, myactor.generated.h, class name, AMyActor.
Something just like that. A structured way to hold the parsed results.
And the process header file function finishes by returning a list of these class info dictionaries.
Yes, it returns that list. It could be empty if no matching classes were found in the header, or it could contain one or more dictionaries if it found multiple UClass definitions in that single file. This list is the crucial output of the parsing stage.
Okay, another micro recap then. Process header file is our parsing engine. It takes the header file path, validates it, reads the C++ code as text. Then it unleashes this powerful, specific, regular expression to find lines that look like UCL, followed by class name dot public parent name. It extracts the class name, parent name, and optionally the API macro using capturing groups. If the API macro isn't captured, it tries a path-based guess. It also uses a lookup table to figure out the likely generated header name for common parent types. All this extracted and derived information for each found class is bundled into a dictionary. The function returns a list of these dictionaries. This list is the blueprint, this set of instructions detailing what code needs to be generated in the next step. Perfectly summarized, it translates the unstructured C++ text into structured data ready for the code generator. All right, Chapter 3, generating the .generated.h file. We're moving to the generated flexion files, class info function. This takes that list of class info dictionaries we just meticulously assembled.
Right. Now we switch from reading and analyzing to actually writing files. This function takes the blueprint and builds the C++ code.
It probably starts by setting up some counters and tracking variables.
Yeah, you'd expect generated art count = 0, generated CP count = 0, and importantly, probably a set called something like processed generated.
Why a set?
Because a set only stores unique items. Remember, multiple UCL classes in the same source header file should all result in the same single .generated.h file being created. We only want to write that file once. This set lets the script keep track of the .generated.h file paths it has already created during this run.
Prevents duplicate writes. Makes sense. And maybe something similar for the .cpp files.
A bit different for .cpp. Since multiple classes from one header go into one .generated.cpp, you need to accumulate content. So you'd likely see a dictionary or maybe generated CPP content map. The keys would be the .generated.cpp file paths, and the values would be lists of strings, where each string is a line of code to be written to that file.
Okay, so a map to collect lines per output CPP file. Got it. The function then loops through each info dictionary in the class infos list we passed in.
Correct. For info in class infos, it processes one class's info at a time.
Inside the loop, it unpacks the data from the info dictionary.
Yes. Header path, info header path, class name, info class name, info parent name, app, macro, info app and macro, and so on. It also needs the file names derived from the path, like header file name, header path.name, myactor.hh, header stem, headerpath.stem, myactor, and generated include file name headerstem.generated.h.
And it calculates the full output paths for the generated files using pathlib.
Yep. Header headerpath.parent gets the directory. Then generated path header generated include file name and generated CP path header fheaderstem.generated.cpp. Using the operator with pathlib objects is really clean for joining path components.
Okay, let's focus purely on the .generated.h file generation first. There's that check using the set. If generated header path not in process generated.
Exactly. This is the gatekeeper. If this specific .generated.h path is not already in our set of processed files, it means this is the first time we're encountering a class from the source header, so we do need to generate the .generated.h file. If the path is already in the set, we skip the .h generation entirely for this class because it was already done for a previous class from the same source file.
Smart. If it needs to be generated, the first step is ensuring the output directory exists.
Standard procedure, that generated hpath.parent.mkdr. Parent's true, exists true. Gets the directory part of the path, parent, calls mkdir, parents. True creates any needed intermediate directories. Existic? True means it's fine if the directory already exists, no error is thrown. Safe directory creation.
Then it constructs a unique header guard name.
Yeah, something like header guard geld LEOV and id acta name and generated include file name dot replace. It takes the generated file name like myactor.generated.h, replaces the dot with an underscore, converts to uppercase, and prefixes it with something unique. This creates a C++ preprocessor macro name like UEMini Generated Macro Generated.
Used for the traditional hashtag FDEF guards.
Traditionally, yes, although modern practice often favors hashtag pragma once. Defining this unique identifier is still part of the common pattern, and we'll see it used later too.
Okay, now the core part. Writing the actual content to the .generated.h file using withopen. What exactly gets written inside?
It typically starts with some standard comments, maybe a copyright notice, and definitely a warning like, this file is automatically generated, do not eat it.
Good warning.
Hashtag pragma once. This is the modern, simpler way to tell the compiler, only include the contents of this file once per compilation unit, preventing redefinition errors. Most compilers support it.
What includes go in?
Hashtag include core minimal.h is almost always first brings in the absolute essential engine types and macros. Then, critically, hashtag include header file name.
It includes the original header file itself.
Why? Because the generated code in this file is adding declarations related to the class defined in your original header. For the C++ compiler to understand those declarations, like adding a StaticClass member function, it needs to have already seen the definition of the class itself. So the generated header must include the original header it corresponds to.
Okay, that makes sense. What else?
It needs to include the generated header for the parent class. So you'll see logic like if parent ederstem and parent ederstem object, parent generate include parent ederstem.generated.h, hashtag include parent generated.
Generated header.
Because the code injected by generated body often relies on things set up by the parent's generated body. For example, your class's StaticClass implementation will eventually need to know about the parent's UClass, which is accessed via the parent's StaticClass. The necessary declarations for the parent's reflection setup are likely in its generated header. It builds an include chain that mirrors the C++ inheritance chain, the check parent header stem. Object is probably there because UObject is the ultimate base, and its reflection setup might be handled differently in the core engine, not via a typical generated.h in this minimal system.
Got it. Includes core minimal, the original header, and the parent's generated header. Then comes the main event, defining the generated body macro.
Exactly. This is the primary purpose of this file. It defines a C++ preprocessor macro, often multi-line, using the / character for continuation. Hashtag defines something like macro generated body.
Wait, why that complex name?
Good catch. It doesn't define generated body directly here. It defines a unique file-specific macro first. Let's say the unique header guard was guard me actor generated. It defines hashtag define guard macro generated body. The content of this unique macro is
StaticClass APOU object outer const fname a name const override specialized implementation later return null PTIA.
Wait, no, that's CPP, just the declaration logic. Static register natives.
Let's back up. What goes inside the macro definition, the .generated.h? Just declarations, right?
You're absolutely right. My mistake, jumping ahead. The definition in the .generated.h file provides the declarations that generated body should expand to inside your class. So that uniquely named macro would expand like this.
Declare StaticClass. Declare StaticClass, void static register natives, hashtag class name. Declare static register natives, often namespaced. Okay, so it ensures the code injected by generated body is public, declares the StaticClass function, declares a static register natives function, often with the class name appended to avoid clashes, and then switches to private.
Exactly. It declares the interface members required for reflection. Static register natives is where, in a full system, U-function registration would happen. Here, it's just declared.
So the generated body macro I put in my source file, myactor.h, isn't the actual code. It's just a placeholder.
Precisely. It's a placeholder. And the trick to making it expand to these declarations happens after this unique macro is defined. The .generated.h file then does this. Hashtag undef generated body. Hashtag define generated body. Guard me actor generated body.
Explain that undefined or defined step again.
Okay, picture the compiler processing your myactor.h. It sees class amyactor.publicactor class generated.h. The build system ensures that myactor.generated.h gets included after the class definition is seen, but before the compiler fully resolves everything. When myactor.generated.h is included, 1, it defines that unique macro guard myactor.generated.actor generated body containing the public static class declarations. 2, hashtag undef generated body. It removes any previous definition of generated body the compiler might have seen, for example, from core minimal or a parent include. 3, hashtag define generated body, guard mactor generated body. It redefines generated body to expand to our unique macro name. Now, when the compiler finally expands the generated body macro inside your amyactor class definition, it uses this new definition. And what does guard mactor generated body expand to? It expands to those declarations there.
Imagery. So the .generated.h file acts like a set of instructions slipped to the compiler after it reads your class definition. It says, hey, forget any old definition of generated body. From now on, for this class, whenever you see generated body, replace it with these specific function declarations. It's essentially injecting the required reflection interface members into your class.
That's a perfect analogy. It augments your class with the necessary interface.
After writing this .generated.h file content, the script prints a confirmation message.
Yep, generated h myactor.generated.h.
Adds the generated add path to that process generated set to prevent writing it again.
Process generated.h.add generated h path.
And increments the generated h count.
Generate h count plus il1.
Okay, let's do another micro recap. We've now conceptually generated the .generated.h file. Its key role is to be included by the build system after your original class header definition. It includes necessary base headers, your original header, and the parent's generated header. Its most crucial job is to redefine the generated body macro. This macro, when placed inside your UClass definition, now expands to declare the required static functions like StaticClass and static register natives, making them part of your class's public interface before potentially adding a private specifier. This is the declaration half of the reflection code generation defining the interface.
Excellent summary. It lays down the contract that your class will fulfill for the reflection system.
Right, Chapter 4. Generating the generated.cpp file, Part 1. Let's move on to generating the implementation code that goes into the corresponding .generated.cpp file.
Right. Still inside that main loop, iterating through each class info dictionary found during parsing. Now, the script focuses on accumulating lines of C++ code into that generated CPP content map we talked about earlier. Remember, the key is the path to the generated.cpp file, agmyactor.generated.cpp, and the value is a list of strings, lines of code.
Before adding class-specific stuff, there's a check you mentioned. If class name is UObject, continue. Why skip UObject again?
Just to reiterate, UObject is the root of the whole UObject system. Its own setup is usually fundamental, built into the engine's core C++ code, not generated by a typical header tool. This script is for generating code for classes that derive from UObject or its children, not for UObject itself. So if the parser somehow found UClass on UObject, unlikely in reality but defensive coding, this skips generating any .cpp content for it.
Okay, makes sense. If it's not UObject, the script needs to add content to the list associated with its .generated.cpp file path in the map. It first checks if this is the first class being processed for this particular .cpp file.
Exactly. If generated CPP path, not in generated CPP content map. Since one generated.cpp file holds the implementations for all UClasses from the corresponding source header, we only want to add the common file level includes once, the first time we encounter a class belonging to that .cpp file.
So if the path isn't in the map yet, it initializes the list for that path.
Yes. Generated CPP content map generated superlabel path, and then it appends the standard includes needed for almost any generated.cpp file.
Boilerplate comments first, like copyright and generated file.
Yep. Then the includes, #include core minimal.h, always needed, #include uObject object macros.h, contains various low-level macros used by the uObject system, #include uObject class, provides the definition of uClass itself, which we'll be creating, #include uObject to object globals, gives access to global functions like StaticClass, lookup, and crucially, the register class function we'll need later.
And it also includes the original header file again.
Yes, absolutely vital. This .generated.cpp file is going to define member functions of your original class, like amyactor.StaticClass. To define members of a class, the compiler needs to see the full definition of that class. So just like the generated.h, the .generated.ctp must also include the original header file.
Okay, so these initial includes provide the context, core types, uObject internals, globals, and the definition of the class itself.
Exactly. Everything needed for the generated implementation code to compile and link correctly.
After adding those common includes, if it's the first time for this file, the script then appends the C++ code specific to the current class name being processed in the loop.
Right. It grabs the list of lines for the CP path from the map. CPP content generated CPP content map generated CP path. Then it starts appending class-specific lines to CPP content.
Probably starts with a marker comment.
Good practice. CPP content.append f-start class name bound helps delineate code for different classes within the same generated file.
Then comes the implementation of static register natives.
CPP content.append foid class name.sana. Static register natives class name. Remember, the .generated.h declared void static register natives class name. This line provides the definition.
But the body is empty.
In this minimal script, yes. A full engine tool like UHT would parse your ufunction macros and generate C++ code inside this function's body to register those functions with the reflection system, making them callable from script or network replication. This minimal version just provides the empty function definition to satisfy the declaration made by generated body, fulfilling the structural contract without implementing the full feature.
Okay, satisfies the compiler. Next, we encounter the definition of a helper struct, often prefixed like zconstruct. Let's call it zconstruct uClass name statics.
Imagery, exactly. Think of this as a dedicated static associated with the type, not instances, utility box just for class name. The zconstruct prefix is a common convention in generated engine code for helpers related to construction or reflection setup. It holds pieces needed once to build the UClass object.
What's defined inside this static struct?
Two key things usually. First, a static helper function. Static UClass outer class. Return parent name StaticClass.
It's his job.
Elaborate. Its sole purpose is to provide a reliable way to get a pointer to the UClass object of the parent class. When the engine builds the reflection data for your class name, it needs to link it correctly into the inheritance hierarchy. Knowing the parent UClass is essential for that. This function achieves it simply by calling the parent's own StaticClass function. Since the parent is also a UCLS, the code generation guarantees it also has a StaticClass function that returns its unique UClass object. It's a crucial link in the chain.
What about error handling? What if parent name was somehow missing?
A robust script might add a check. If parent name was empty, which shouldn't happen if the regex worked, it might return null PTR inside outer class, and maybe add a hashtag error comment to alert the user during compilation.
Okay. What's the second thing inside the static struct?
The most important part, static UClass class pointer. This declares a static pointer variable within this helper struct. This pointer is the designated spot where the single unique instance of the UClass object representing class name will be stored once it's created. This is central to the singleton pattern for UClass objects.
A static pointer member. And it needs to be initialized, right?
Yes. Immediately after the struct definition, you'll see the actual definition and initialization of the static member. UClass zconstruct UClass class name statics class pointer equals null PTR.
Why initialize it to null PTR?
Elaborate. This signifies that initially, the unique UClass object for this specific class name has not been created yet. It will only be created on demand the very first time code calls class name StaticClass. Setting it to null PTR is the starting state for the lazy initialization used in the singleton pattern.
Okay, let's pause again. Micro recap time. We're digging into the .generated.cpp file generation. We saw the common includes added once per file. Then for each class, we add an empty static register natives implementation. Critically, the script then defines a static helper struct, zconstruct UClass class name statics. This struct serves as a container. It holds a static pointer, class pointer, initially null, which will eventually point at the one and only UClass object for class name. It also provides a static helper function, outer class, to easily get the parent class's UClass object. This struct is essentially setting up the storage and linkage needed before we actually create and access the UClass singleton object itself.
Perfect recap. It prepares the static infrastructure for managing the unique UClass instance.
Vector 5. Generating the .generated.cpp file, part 2. Continuing with the .cpp content for our specific class name. What comes after the static struct definition and initialization?
The next major piece is the definition of a specialized C++ class that actually inherits from the engine's base UClass type. It's often named similarly, like class, UClass name, public UClass.
Imagery. Okay, so if UClass is the generic blueprint for class reflection data, this UClass class name is like a custom printed version of that blueprint, specifically tailored for our class name.
That's a great analogy. It inherits all the general UClass functionality, but overrides certain behaviors to be specific to the C++ type class name it represents.
What's the most important behavior it overrides?
Usually, the key override is the construct object method. Virtual UObject, construct object, UObject outer, const fname and name, const override.
Why is construct object so important?
Elaborate. Think about how the engine creates objects. When you call new Objectimi actor in C++5, or when the engine spawns an actor from a blueprint based on your AMI actor class, it often works through the UClass system. It gets the UClass object for AMI actor and tells it, hey, construct an instance of the C++ class you represent. The construct object virtual function is the mechanism UClass provides for doing exactly that. It's the bridge from the reflection data back to actual C++ object instantiation.
So how does this generated specialized UClass class name implement construct object?
This is where the magic happens. Its implementation looks something like this. Return new object class name. Outer static case UClass. Const cast UClass name.
Whoa, break that down.
Elaborate smoke. The UClass name type knows implicitly which C++ class it stands for, your class name. So its implementation of construct object directly calls the engine's templated new object function. Crucially, it provides your actual C++ class type as the template parameter to new object. This ensures that the correct C++ type is allocated and constructed. It forwards the outer argument for specifying the owner of the new object and the desired name for the new instance. The StaticClass UClass class part is just handling the C++ type system. It's casting this pointer, which points to the current UClass class name object, to the plain UClass that new object expects as its class context parameter.
So the engine generically calls construct object on a UClass pointer, but because it's actually calling it on our specialized generated UClass class name instance, that instance knows to call the correct new object class name C++ template function.
Exactly. It connects the generic engine object creation mechanism back to type-safe C++ template instantiation for your specific class. It's the type-aware factory method provided by the reflection system.
Very cool. Okay, so we have the specialized UClass type. Now, what about the implementation of the StaticClass function itself, the one declared in the .generated.h via generated body?
Right. Now we provide the definition for UClass, class name StaticClass.
Elaborate. This is the actual C++ code for that static function that belongs to your original class name. This is the function everyone calls to get the unique UClass object representing class name. What's the core logic inside this function's definition?
It implements the singleton pattern using the class pointer we set up in the static struct. The first line is the check. If construct UClass statics not class pointer. Elaborate.
So it checks if that static class pointer is currently null PTR. If it is, what does that mean?
It means this is the very first time StaticClass has been called for this specific class name during the program's execution. The unique UClass object hasn't been created yet.
So if the pointer is null, the code inside the if block runs to create it.
Precisely. The line inside the if block looks like z construct uclassing class name statics, class pointer new uclass name txt class, c constructing statics outer class.
Break that one down too.
Elaborate. Okay, if the class pointer was null, 1, it calls new uclass name. It dynamically allocates a new instance of that specialized uclass name type we just discussed. 2, it passes 2 arguments to the constructor of uclass name. The name of the class as a string literal, using the textxt macro for engine string handling. Z-construct uClass class name statics, outer class. It calls that static helpful function from the static struct to get the uClass pointer for the parent class. 3, the pointer returned by new, pointing to the newly created uClass class name instance, is then assigned to and stored in the static Z-construct uClass class name statics, class pointer.
So it creates the unique instance using the specialized type, giving it its name and parent, and stores the pointer in that static variable.
Exactly.
And what happens if the class pointer was not null when StaticClass was called, meaning it had been called before?
Then the if class pointer condition is false, and the code inside the if block is simply skipped. The function proceeds directly to the last line,
Which is?
return zconstruct uClass class name statics dot class pointer. Whether the pointer was just created inside the if block or whether it already existed from a previous call, the function always returns the current value stored in that static class pointer.
Ah, the singleton pattern in action. First call creates and stores. Subsequent calls just return the stored pointer. Guarantees only one uClass instance exists per C++ type.
That's the core idea. It provides lazy, thread-safe, in more complex engine implementations, often using atomics or other locking, initialization and access to the unique uClass object.
Can we quickly verbalize the algorithm for StaticClass?
Sure. It's a classic lazy initialization singleton. 1. Check the static class pointer associated with this class type stored in the statics helper struct. 2. Is the class pointer currently null PTR? 3. If YES, first time called, JA, get the parent class's uClass by calling the statics outer class, helper function.a. Get the parent class's uClass by calling the statics B. Create a new instance of the specialized uClass class name using new, passing the class name string and the parent uClass to its constructor A. Get the parent class's uClass by calling the statics C. Store the pointer to this new instance in the static class pointer. 4. If NO, called before, or after creating it in step 3. 4. If NO, called before, or after creating it in step 3a, return the pointer currently stored in the static class pointer.
Okay, this section was super important. Micro recap time again. We defined the specialized UClass class name subclass, which crucially overrides construct object to know how to create instances of your specific C++ class using new object your class. Then, we implemented the StaticClass function declared by generated body. This function acts as the gateway to the unique UClass object for your type. It uses a singleton pattern. Check a static pointer if null, create the specialized UClass class name instance using the name and parent UClass, and store its pointer, then return the pointer. This ensures class name. StaticClass always returns the same single UClass object. This provides the definition and core access mechanism for the reflection implementation.
Exactly right. We've defined the reflection object and the standard way to get it.
Chapter 6. Generating the .generated.cpp file part 3 and final write. We're almost at the end of the generated C++ content for a single class. What's the final piece needed in the .generated.cpp?
The final piece is ensuring that this UClass object we can now create via StaticClass actually gets registered with the engine's global systems so the engine knows it exists and can find it.
How's that done? Another helper struct.
Usually, yes. Another static helper struct, often named something like registration info UClass class name.
Imagery. If the static struct was the storage box and UClass class name was the custom factory, this registration info struct is like a tiny, self-deploying registration agent. Its whole purpose is to announce the class to the engine.
That's a perfect description. Its power lies in its constructor. Registration info UClass name.
Why is the constructor special here?
Elaborate. Because, as we'll see, we create a static global instance of this struct. In C++1, constructors for static global objects are automatically executed very early during the program's startup sequence before your main function, or the engine's equivalent entry point, even begins running. This automatic execution at startup is the key mechanism.
So what does this constructor do when it runs automatically?
It typically performs two critical actions inside its body. One, UClass class PRR get let class name, StaticClass. It calls the StaticClass function we just defined for class name. Remember, the first time StaticClass is called, it triggers the creation of the unique UClass object if it doesn't exist yet. So this line ensures that the UClass object for class name gets created, if needed, right here at program startup. 2, if class PTR uObjectGlobals.register class PTR register class, it checks if StaticClass returned a valid pointer. It should have. If it did, it calls a global engine function, usually something like uObjectGlobals, register class, passing the UClass pointer, class PTR.
And register class does what?
Elaborate. This is the final step. Register class tells the engine's central uObject registry, here is a UClass object representing a type, add it to the list of known types. Once registered, the engine can find this UClass by name, for example, for spawning, list it in the editor's class viewers, use it for serialization, etc. It makes the class officially known to the runtime.
So the static registration struct's constructor forces the UClass to be created via StaticClass, and then immediately registers that UClass with the engine's global system.
Exactly.
But how does this constructor get called automatically at startup? You mentioned this static global instance.
Yes. Right after the definition of the registration info class name struct, you'll find a line that simply declares an instance of it. Static registration info UClass class name, registration info UClass class name instance.
Explain that line's impact.
Elaborate. This line declares a variable named registration info class name instance. The key parts are static and its placement at global scope outside any function. In C++, objects with static storage duration declared at global or namespace scope undergo static initialization. This means the C++ runtime system guarantees their constructors will be executed before the program's main function starts. The exact order between different compilation units can be complex, but the constructor will run during the program's loading and initialization phase. So, by merely declaring the static global instance, we ensure its constructor, registration info UClass name, runs automatically, triggering the StaticClass call and the register class call for this specific class very early on.
Wow, that's really clever. It's a C++ mechanism leveraged for automatic, decentralized registration. No single master list needs to be manually updated. Just compiling this generated code ensures the class registers itself.
It's a very common and effective pattern for systems like this, where components need to announce their presence to a central registry automatically.
Okay, after the registration instance is declared, does it add a closing comment marker for the class?
Yes, typically cpp content.append, FSEND class name, to clearly mark the end of the code generated for this specific class within the .cpp file.
So that completes the C++ code generation for one class. Now remember, we were appending all these lines, common includes, and then code for class 1, then code for class 2, etc., into lists stored in the generated PPP content map. The script needs to actually write these files now.
Right. After the main loop over class infos finishes, the script needs a final loop for CDPP path content lines in generated CPP content map.items.
Elaborate. Explain this loop's purpose again.
This loop iterates through the items in our generated CPP content map. Each item is a key value pair. The key CP path is the full path to a specific .generated.cpp file, and the value content lines is the complete list of all the code lines. Common includes plus the start-end blocks for every class belonging to that source header that should go into that file. This loop ensures each .generated.cpp file is written exactly once, containing the aggregated content for all relevant classes.
Inside this loop, it first ensures the directory exists.
Same as before, cpkeypath.parent.mkdr, parent's true, exists to true, safe directory creation.
And then it writes the collected lines to the file.
With OpenCPPath.wo encoding UF8 as FFWrite, join content lines, it opens the file in write mode, WOS, specifying UTF-8. The crucial part is N join content lines. It takes the list of string lines and joins them into one single large string, putting a new line character N between each original line. That complete string is then written to the file.
Prints a confirmation message.
Print f-generated CPP path.relative tepathat.cwd.
And increments the generated CP count.
Generated CPP count plus equals 1.
And finally, after this loop finishes writing all the .generated.cpp files, the generator function files function returns the total generated H count and generated CP count back to main.
Exactly, which main then uses for its final success message.
Wow. Okay, final micro recap for the .cpp generation's last part. We wrapped up the content for each class with the crucial static registration mechanism. A helper struct z registration info has a constructor that calls StaticClass, forcing UClass creation, and then UObject global's register class. A static global instance of this struct instance is declared, which makes C++ automatically run its constructor at program startup. This ensures every UClass registers itself with the engine before anything else happens. Finally, the script iterates through the map where it collected all the .cpp lines, joining the lines for each file, and writing the complete .generated.cpp files to disk. This completes the entire code generation process, providing the necessary definitions, the singleton access, the specialized construction, and the automatic registration hooks for your UClasses.
You nailed it. That covers the entire journey from parsing the header to writing the final implementation and registration code.
Okay, let's do the end-of-source mega recap. Bring it all together. We conceptually walked through a Python script, a simplified model of an engine build tool. Its input is one or more of your C++ header files provided on the command line.
It parses these headers, primarily using a complex regular expression pattern crafted to find UClass macro declarations, immediately followed by class name, public parent name definitions. It carefully extracts the class name, parent name, and potentially an API export macro, with some path-based guessing as a fallback.
For each UClass it successfully parses, it gathers this information and prepares to generate two companion files, typically placed right next to your original header. .generated.h and .generated.cpp.
The generated.h file's main purpose is to be included after your class definition. It includes necessary core headers, your original header, and the parent's generated header. Its most critical function is to cleverly redefine the generated body, macro, so that when the compiler expands it within your class, it injects the required declarations, specifically static UClass, StaticClass, and static void, static register natives.
The .generated.cpp file provides the definitions for those declared functions. It defines StaticClass using a singleton pattern, ensuring only one unique UClass object exists per type. It defines a specialized internal class, UClass name, inheriting from UClass, which overrides construct object to know how to create instances of your specific C++ class using new object class. It also defines the, in this minimal case, empty static register natives function.
And crucially, the .generated.cpp includes that static registration mechanism, a struct, Z registration info, whose constructor calls StaticClass and register class, and a static global instance of that struct, which ensures this registration happens automatically when the program loads.
This whole generated structure provides the minimal infrastructure for reflection, primarily enabling the StaticClass functionality, getting the runtime type object, and basic object construction via the UClass system using new object.
Connecting this back directly to you, the game developer listening, this generated code, or code very much like it, is the invisible foundation that makes so many engine features work. When you see your custom C++ classes in editor dropdowns, when you spawn actors based on a UClass, when the details panel shows info about your components, it's all leveraging the UClass objects and registration hooks set up by code generated similarly to what we've just dissected.
So while the Python script we discussed is a simplified illustration, it reveals the fundamental patterns. Understanding this process demystifies why you need generated body in your UClasses. You now have a much clearer mental model. Generated body is a macro placeholder that expands to declarations defined in a .generated.h. Those declarations are implemented in a .generated.cpp using singletons and specialized classes, and a static instance in that .cpp makes sure the whole thing registers itself with the engine at startup.
Let's quickly hit the key concepts like flashcards, source tool, hypothetical Python script, modeling engine build tools, input, C++ header files via command line, output.generated.h, and generated.cpp files per source header. Key macro parsed, UClass in context of Cloudlick, core regex role, scanner looking for the specific UCS class inheritance pattern, .generated.h purpose, declares reflection functions, StaticClass, static register natives, redefines generated body macro to inject these declarations. Generated.h includes core minimal.h, original header, your class.h, parents generated header, parent.generated.h, generated.cpp purpose, defines reflection functions, StaticClass implementation, static register natives body, defines specialized UClass subtype, triggers automatic class registration, StaticClass implementation, singleton pattern, returns unique UClass object, creates it via new UClass class name on first call using name and parent UClass, UClass class name role, specialized UClass subclass knowing how to construct object for its specific C++ type using new object class name, static registration instance, static Z registration info class name instance. Its constructor automatically runs at startup, calling StaticClass, then register class. Minimal feature focus. Primarily static class functionality and enabling basic object construction via construct object new object. Does not cover properties, ufunctions, etc.
So that was our deep dive into a minimal but illustrative code generation tool for C++ reflection. It demonstrates how a script can automate the creation of necessary boilerplate C++ code by parsing source files, using techniques like regex, and leveraging specific C++ language features like static members, macros, singletons, and static initialization to integrate your types with an engine's runtime systems.
Hopefully the next time you write a new UC class for your game, you type generated body and hit compile, you'll have a much deeper appreciation for the machinery whirring behind the scenes, the generated header injecting declarations, the generated source file defining the static class singleton and the construct object factory, and that little static instance making sure the engine knows about your class from the get-go.
It definitely removes some of the magic feeling. Now, for a final provocative thought to leave you with, we've seen how this minimal approach handles StaticClass and basic construction, considering the full spectrum of reflection features in modern engines like exposing C++ properties, the U property, to the editor blueprints, exposing C++ functions, U function to be called from blueprints, handling network replication, serialization, garbage collection references. How much more complex do you think the parsing logic and especially the generated code in those .generated.h and generated.cpp files would need to become to support all of that? What kind of structures and registration calls would be needed? Something to ponder as you work with these more advanced features.